Okay, in the third part of my second part of my forces video series, 2C, we're going to look at weight, mass, and acceleration due to gravity. Weight being Fw, the variable, and the unit is Newton. M being the variable for mass, and the unit is kilograms. And G being the acceleration due to gravity, which is any acceleration is going to have meters per second squared. It just happens to be a specialized one. On Earth, that's close to 10 meters per second squared, but it's going to change in this lesson because we're going to go other places than Earth. This equation, your weight, actually comes from the force of gravity, which is a product of masses, two masses, the distance between the masses, and this is not small g. This is a universal gravitation constant. So 6.67 times 10 to the negative 11th. A very small number, negative 11th, because it's a very weak force. So if you are just comparing your weight, where does your weight come from? Well, it's your mass, the Earth's mass, and the distance between you and the Earth, which actually is, since you are very small relative to the Earth, we're just gonna go with the radius of the Earth if we ever have to solve that. Okay, we're going to use the product of all that. We're going to look at the weight equation. The weight is nothing more than a specialized F equals ma, but in this case, the force is the force of gravity on you, causing the force of gravity causing an acceleration on your mass. And so it's just a comparable equation. Fw equals mg. Okay, so let's take a look at what these two things are and how they're different. Well, mass is nothing but a measurement of all your atoms that make up your body. This is not going to change no matter where you're at. If you're on the moon, you got the same mass. If you're on the Earth, you got the same mass. If you are weightless in space, you still have the same mass. You're still you. Weight is going to be a measurement of the pull of gravity. In our equation, it's going to be a product of not your mass, because mass stays the same, but the gravity that you are feeling depending on where you're at, the acceleration, the pull of that acceleration, depending on where you're at, the result of that pull. Okay, on Earth, gravity is about 10.10 meters per second squared. That's because the mass of the Earth is pretty big, 5.972 times 10 to the 24th kilograms. Whereas on the moon, we're a little bit smaller, 7.348 times 10 to the 22nd. So we'll look at that number when you're comparing. That's going to be more, have more to do with this moon size being smaller. And therefore, the result is the acceleration due to gravity on the moon is going to be 1.6 meters per second squared. It's going to be much smaller as well. Okay, now we have our little Natalia over here. She's waving at us from the Earth and from the moon. She has a mass of 76 kilograms, which is not going to change. She's 76 kilograms here. She's 76 kilograms here. That's her mass. Once again, doesn't change. It's the weight that's going to change because of the, once again, it's really due to the mass of the Earth versus the moon and versus her, the mass of the moon versus her. But it's due to the acceleration that results from that. So what is her weight on Earth where the acceleration due to gravity is 10 meters per second squared? Well, we're going to do the Fw equals mg equation. Her mass is 76. The acceleration due to gravity is 10. So she would have a weight of 760 newtons. Once again, weight is in newtons, mass is in kilograms. So 760 newtons. And if you're ever given a newton on Earth, you can divide by 10. That's a pretty good number, or 9.8, and you'll get the kilograms instead. But here, we're going from mass to weight, so we're multiplying by 10 on Earth. Well, on the moon, which is much smaller right here, acceleration is 1.6, so the g is 1.6 meters per second squared. So in this case, Fw equals mg. Well, our mass is the same, but 1.6 is the acceleration due to gravity on the moon. So 76 times 1.6 equals, and that ends up being 121.6 newtons, so much less weight on the moon. She went to Neptune. We got a new gravity, but the same mass. Her gravity would be 11.14. Once again, Neptune, the acceleration of gravity of any object on Neptune is going to be 11.15. And so 11.15 times 76 equals, she would be 847.4 newtons on Neptune. And then just looking at the overall, which changes based on how close you are to another mass. that is going to be weights. Mass does not change. Her mass is 76 kilograms on the Earth, 76 kilograms on the Moon. But because FW equals m times g, which g does change, once again right here, the weight would change as a result. So the bigger the planet, the more massive it is, the more weight you would have on that planet. Okay, so back to this question. In this question, if the Earth was twice as massive, how would the acceleration felt by Natasha compare? We actually have to get to this equation. Fg equals capital G m1 m2 over d squared. We'll look at that a little closer later on. And if everything was the same, G being the same, m being the same, m2 being the same, d being the same squared, and then when we take a look, we're going to have to put this over this. Once again, this is the equivalent. M1, M2 over d squared. So this is the new, this is the old. Once again, 1 times everything would be the g was the same, mass was the same, mass was 2 was the same, distance was the same, distance was the same squared. So that's that, and that actually equals 1. And then the new setup, I have the same g. G is a universal constant. It's always going to be 6.67 times 10 to the negative 11th. But in the case of law of ones, it is exactly what it was before, so it gets a 1. The mass of one of those objects, let's say that was Natalia, was the same, but the Earth was twice the size. Distance is the same. How would that compare? It would be the force of gravity. Once again, here we'd have to start with the force of gravity. The force of gravity is going to be 2 times. Now we do that last step, F equals ma, A equals F over m. So let's put that over force over mass if everything was the same, it'd be 1 over 1, so it'd just be 1 on the bottom. But if the force was twice as much, the mass being the same, Natalia would feel an acceleration of 2 times what it was before. So hopefully this helped.